In this video, I will briefly introduce chi-square analyses for hypothesis testing. In most clinical or epidemiological studies, we're interested in testing whether there's a relationship between our independent variable or exposure and our dependent variable or outcome. We use chi-square analysis to test the null hypothesis of no association when both our independent and dependent variables are categorical. For example, we might be interested to know whether the likelihood of a heart attack differs among three categories of BMI: low, normal, or high. In our overall study sample, regardless of BMI, we would have a frequency distribution of heart attack that might look something like this. We can then look at that distribution by categories of BMI as shown here. In this case, the proportion of people with heart attack is similar between all three BMI groups. We might also see something like this, where the proportion of those having a heart attack looks different based on which BMI category people belong to. The question is whether any difference we see is statistically significant. Conceptually, with a chi-square test, we're testing the null hypothesis that the frequency distribution for one categorical is equal across the groups of a second categorical variable. This is another way of looking at the relationship between two categorical variables. The table shows the number of people with and without a heart attack based on BMI group. If there was no relationship between BMI and heart attack, we would see something like this, where the distribution of heart attacks is equal across BMI groups. If there was a difference in the likelihood of a heart attack across BMI groups, our data might look something like this. This is the formula for the chi-square test statistic. O means observed count, and E means expected count. Say this table represents the data we actually get in our study. Each cell in the study had an observed count. For the top left cell, this is 20, etc. This is the O in our formula. The E for expected count is the number we would expect in each cell if the null hypothesis was true. In other words, it's the count we would expect for each cell if there was no difference in distribution of heart attacks across BMI groups. We get the expected count for each cell by first calculating the row and column totals. We then calculate the percent of heart attack cases in the overall sample, which in this case is 50%. We multiply these percentages by each column total to get the expected cell counts. In this case, we have an expected count of 15 in each cell. This is what the data would look like if the null hypothesis was true. For every cell, we then calculate this formula. The observed count, which is what we see in our actual data, minus the expected count from what we expect under the null hypothesis, squared, divided by the expected count. Intuitively, this means that the greater the difference there is between what we observe in our data and what we would expect if the null hypothesis was true, the higher the chi-square test statistic and the greater the likelihood we're going to reject the null hypothesis. One more time, we're saying that the more our data differ from what we would expect based on the null hypothesis, the more likely we are to reject the null hypothesis. For the first cell, our observed count is 20. Our expected count, if the null hypothesis were true, is 15. We plug these numbers into our formula to get the value for observed minus expected squared divided by expected. So in this case, we have 20 minus 15 squared divided by 15, which ends up equaling 1.67. We do this for every cell, and then we add things up. In this example, our total ends up being 6.67. We can then take a look at a chi-square table to see our p-value for that chi-squared statistic value. The p-value is the probability we would see a chi-square value of 6.67 when testing the relationship between a 2-category and a 3-category variable if the null hypothesis were true in the underlying population. In this case, our p-value is less than 0.05.